So the next talk will be by Tryphon, Georgiou from UC Irvine. So he will talk about constructing bridge with unbalanced marginals.
Thank you very much, Wilfried. I would like to thank Simone and Katie for a wonderful workshop and giving me the opportunity to be here. And I'm looking forward to meeting all of you and having the chance to chat during the week. It's an absolutely wonderful place and an excellent environment for all of us. So I'll be talking today about the title, you can read it there, the most likely evolution of diffusing and vanishing particles in the spirit of Irvine Schrodinger. It's about coupling distributions with unequal marginals. It's joint work with Yongxin Chen, who is the heart of the team. He's here, and Michele Pavone. I plan to give you a little bit of context and motivation for interpolating distributions with unequal marginals. Then I'll move on to optimal mass transport very briefly, and its sibling, the Schrodinger bridge problem, or regularized optimal transport. And we heard a very interesting, very nice talk by Augusto just now. So it's nice segue here. And then I'll tell you about exactly the new insights of this work on coupling distributions and balanced marginals in the spirit of Schrodinger, going back sort of like to the horse's mouth, some of the spirit of the original motivation. So the coupling between distributions and the buzzword is morphing, conjures, for those of you that have seen Terminator 2, conjures up images of this, this playful reference to this liquid metal that it's a futuristic contraption that transforms to any shape. But of course, the density is not, mass is not preserved along this. And even though we don't make any claim of competing with the film industry, similar problems arise have arisen very often in many application areas. And this over here is a little bit of a reference to some applications that motivated our group to look into optimal mass transport back in the around 2005, 6, and so on. Again, coupling distributions that have an equal mass. So the picture over here that you see represents a tracking with some radar. So here you have the signal, and the blue segments here, you have a spectrogram. So this is sort of the information that you can pull out of that. And this here is some geodesic in optimal transport sense, linking all of these sample points, which pictorially can be shown here in a non-parametric way to capture exactly the Doppler shift of a moving object. This is a morphing of speech. I will skip further details of that. This goes quite far back. And this is some sort of a smoothing of a spectrogram of a temperature field for non-invasive sensing. So the bottom line is, no matter how you look at it, in some applications, for example, in spectral analysis, the power spectrum of a time series at one point in time and another doesn't have enough the same power. So you in order to link those with, let's say, optimal transport geodesic, of course you can normalize, but that's not quite natural because you're interested in capturing how the energy shifts across frequencies. And the same applies with images. So that naturally led us back then to study the work that was already exploding in optimal transport, and this is a completely incomplete, reference to all in this workshop. You're very well aware of optimal transport and the history. So back then, prior to 2010, we played with the idea of mixing different metrics. For example, in interpolating distributions, let's say this is a density 1 and this is a density 2 that don't have equal masses. So the masses, these are measured. So the notation is a little bit, the F represents here density. Oh, no, actually doesn't represent, sorry, this notation here is kind of inconsistent with so there are two measures here, or densities, and you try to mix some Wasserstein distance between the two with different other metrics that regularize. So for example, here, the one idea that was tried back then is to mix an L1 distance at the start and an L1 at the end, representing errors, and then Wasserstein is in between, so that you get the benefits of weak star continuity. The interesting thing, and I'm not going to refer anymore, discuss this anymore, is that there were interesting dual formulations of such problems that allowed us to interpolate. But again, all of this was a little bit ad hoc. And we come to the 2000 and beyond, which sort of the idea of regularizing Benhamou-Brégnier formulation of matching marginals was blossoming, and there are very many different ideas of setting up convex optimization problems to link marginals. For example, you have two marginals, rho 0 and rho 1, and you might want to satisfy the continuity equation and penalize. This is very much in the spirit of the previous picture. Penalize distance at one endpoint or both endpoints to a perturbed marginal. Or here you have a source term and you penalize the source term in the regularizing function there. Another option which has had quite a bit of usage and applications is you have an expression of this type with, again, it's convex in both S and R. We come to the mid 2000s with Liero, Mielke, Safare. It's a beautiful paper, and many others that fall at the same time that basically explore the mixing of two metrics. So now today's lecture will focus mostly on the Schrodinger bridge problem, which is a sibling of optimal transport, the regularized transport problem, where you have, and I'll talk a little bit about the history of the problem and the rationale before I go into the new ideas that come with this. So this problem is a problem with large deviations, and I'll talk more about this, that leads to an optimization problem of this sort. So you have, in the right-hand side of the continuity equation, you have a Laplacian, and you can put an epsilon there or not. And it's thought of as a regularization of optimal transport, and allows you to use the synchronous algorithm for the solution. And there's much of the theory. Some of this I'll allude to or discuss. There is an interesting time symmetric formulation of it, where you remove the Laplacian from here at the cost of adding this Fisher term in the cost. And there's a lot of work on this, which again, I'm not going to give a complete literature survey here. So let me give you a little bit of going back the history of the Schrodinger problem. So Schrodinger, 1931-32, he wanted to get a physical understanding and a classical understanding of his own equation. So he postulated a certain Gedanken experiment with classical particles, stochastic particles. So he posed the following question. He said, suppose that you have a collection of particles that abide by a certain probability distribution. This is their initial distribution. Let's say, for example, I have a box over here with molecules of oxygen, and I just open it up, and they spread all over the room. They are Gaussian particles. They have to spread all over the place. However, I measure 5 minutes later, and I find them here. You can't tell me they're not there, because that's where they are. it's not consistent with the Brownian diffusion. So something strange happened and they all reassembled there. So he asked the question, how did it go from here to there? So it was an interesting sort of experiment. The mathematics of this took 50 years to be really understood properly and the problem to be posed properly. But Schrodinger, with the limited tools at the time, not only he posed the problem, he solved the problem. His mathematical proof was, this is the answer because it makes sense physically. And it was correct. Of course, it took the rest of us, or the 50 years to understand even the problem. So here is exactly the reformulation of the problem I explained, the statement of the problem that Schrodinger came up with. Cloud of Brownian particles, empirical distributions at 2 points in time, and the empirical distribution is not compatible with the transition mechanism. So of the many possible ways which could have happened, which one is the most likely? So that's a problem in large deviations. This was seen as such by Fulmer, 1988, and it really amounts to the following thing. You have a prior reference measure, which is the Wiener measure, on the path space of the particles. So you have the collection of all possible paths, and R is the Wiener measure. So then you're asking, out of all the probability measures, distributions on paths with the given marginals, which one is the most likely? Which is the one that minimizes the relative entropy to the prior over P's in this set? And this relates to Sarnoff's theorem, and that's the proper formulation. So now the connection to optimal mass transport is simply that if you have a diffusion with a drift here by the Sarnoff's theorem, the relative entropy is essentially a quadratic expression. So, so then the Schrodinger bridge problem can be translated into the problem we just saw in the previous slide. And now the solution of this problem, which again, Schrodinger came up with. He dissected everything in space and time, counted the bins, how many go from here to there, and somehow he came up with the answer. He couldn't justify it, and there was great mathematicians that kept adding to this until 50 years later, where there was a very clear picture of the problem. So the minimizer, and this is the flow of one-time densities, has to be factored into a product, phi star. So this basically relates to gave sort of the idea of this quantum mechanical description of probability being the square of the wave function. So it's kind of analogous, but it's not the same, of course. And these two objects here, two functions, have to satisfy a bunch of equations here. And this is the Schrodinger problem, the Schrodinger system that we saw a little bit earlier in Augusto's presentation, albeit in a slightly different form. So the phi's have to multiply, these two functions, phi and phi hat, have to multiply to ρ0 and ρ1 at the two ends. These are coupled by the boundary conditions, and they have to relate through the prior evolution in this way. So going forward in time, phi hat has to produce phi hat at time t and all the way to the end. And solving in the backward direction, this is the backwards the heat equation. Phi will produce phi 0. So iterating the scheme is basically a synchron iteration. So schematically, this is the initial density given, and the prior law will tell you that it spreads out, but you make a measurement, it's inconsistent, and you would like to match them. So this is the Schrodinger bridge. This is a one-time marginal slices. And the solution that I just outlined is somehow, by hook or by crook, or by the synchron algorithm, you have to break the two distributions into a product, the phi's and the phi hats, and the phi hats propagate according to the heat equation forward, the the heat equation backwards in time, and they have to satisfy this 2-point boundary value constraints. And then the Schrodinger bridge is the product of two distributions, this one and that one, and it gives you the matching. Now, the outline of SB Schrodinger bridge problem theory, of course, this goes further to the situation where you have a diffusion with a drift term and even coefficient in front of the Brownian excitation. Again, I'm kind of repeating the same things, though I'm adding a little bit of notation. So R is the prior of the law there. For every probability law on path spaces, RT represents the marginal at T, and RST represents the joint marginal at T and S. This notation RXY is the law conditioned on the process taking these particular values at the two endpoints. This is what's called the bridge, the pinned bridge. So if you pin it at 2 points, the law on the paths, the mass that sits on the particular, let's say, continuous functions that go from X to Y is provided by this law. In general, if you have a probability law on path spaces, you can disintegrate the measure, and you have the pinned bridge weighed in by the joint marginal at the two endpoints. And you can do this for the prior, or you can do it for the solution, the P that you're looking. So the solution of the Schrodinger bridge problem, which is find the minimizing of the relative entropy between P that is consistent and the R that is not, can be seen very nicely when you start disintegrating the measure. And then you can see that the relative entropy is the sum of these two terms. So this takes the relative entropy of the pinned bridges. And this is between the two endpoints. And the terms are positive, and this one can become 0 when the pinned bridges are identical. So the only thing you need is to find out the adjustment so that the marginals are correct between the joint distributions at the two endpoints. This is the static, and this is the dynamic problems, and this is their relationship. So the relationship is that the solution is the pin bridges, this term stays, and then you have to find the optimal of the static problem. So under natural mild conditions, there exist functions f and g. This can be seen as Lagrange multipliers of the problem of adjusting the two ends. And they are solutions of the Schroedinger system. And then the joint marginal is basically a diagonal scaling of the prior. So you multiply by two functions. And then the same thing is for the law of, so here you have the law on paths, and you have simply to scale it by two functions at the beginning and end. So a little bit more about the Schrodinger system. There is a relationship between this f and the g to the original expressions for phi hat and phi in Schrodinger's formulation. For this more general problem, the Schrodinger system for the two factors of the one-time densities obey the forward Fokker-Planck equation, and this is the adjoint. And very much like in the case of Brownian diffusion, the 2 point coupled nonlinearly at the two ends of the interval. Then again, the one-time densities, which are simply the rho at the time t, is the product of the phi and phi hat, the t time marginals, and these are the law of a diffusion, which is very much like the prior. The prior sits up there, and the diffusion is simply the same, except that you have an added term here that is responsible for matching the two end marginals. So, okay, so now where do we come in this talk? So we are interested in revisiting the problem with losses, unbalanced marginals. And of course, you can add a source term, but again, how do you physically justify this? It depends on the context. So here, we're trying to follow the rationale of Schrodinger, just revisiting exactly the original setting. So again, we postulate that we have particles that are given at 2 points in time. And you can think of them as tracer particles. Like, for example, let's say you have fluid flow, and you'd like to know what happens to the currents. Sometimes, or sediment transport, and experiments like that take place all the time. So you drop particles in, which somehow you can measure later on, and try to find out what happened. And some of those particles, they sit to the bottom and they're gone, they're finished. The same thing happens when, you, for example, you have neutrons that go through some sort of a substance and you expect some effect, and some of them fizzle. So probably that's not a good example, but the tracer example is probably the best one. So you start with an empirical distribution, and then you have a marginal at some point in time later on, but they don't have the same. They are not like this, right? They don't. You have some transition probability, which may also suggest the possibility of losses. You have inconsistency here. But moreover, on top of that, you have the situation that rho1 is less than rho0. And if you'd like to have it the other way around, you can reverse time. It's easy you can have a time symmetric formulation. So the question in the spirit of Schrodinger is this. Again, what is the most likely evolution that accounts for losses? So when you have losses, you need some prior law that accounts for losses, and then you need to adapt that. So the natural thing to have is you have again a diffusion with a prior killing rate. So according to some prior mechanism, particles disappear. So this is called killing rate and relates to Feynman-Katz, and we're going to see the connection or some sort of juxtaposition of the two. So in this context, because we're really looking at the evolution of particles and not taking statistics of any sort, we postulate that the state space is the space where the particles diffuse union a coffin state. When they die, the trajectories disappear, and then they can be seen as being transitioned into that. So then the path here is the Skorohod space of functions from 0 to 1 to x. So there is a continuous path, and then you have a jump to the coffin state. So every path, we can view it as some of them discontinued halfway and jumping to the coffin state according to this law. So now rhos are the original densities, and p's from this point on are natural augmentations where you add mass in the coffin state to account for how many were lost. So you start from rho 0 and 0, and then you have rho 1 and 1 minus the integral. And then the problem becomes this. So it's very similar to the original Schrodinger formulation. So the Fokker-Planck equation for diffusion with killing is, again, the Fokker-Planck, except that you have a term over here that accounts for losses. These are one-time marginals again, and you have this scaling with V that gives you the losses. So now there's going to be again phis and phi hats, which are kind of, you can view them as Lagrange multipliers, trying to solve the optimization problem before, but now you have an additional one which depends on time and space, and one which depends on time, because the state space has expanded. And then this leads to a new Schrodinger system, where again you have the forward evolution for phi hat. Now again, the phi hat is going to have two components. One for the continuous part of the space and one for the discrete, and the discrete accumulates the amount of mass that is lost. And then here you have this, the dual, which turns out to be this, and the matching conditions. And then again, virtually everything works with modulo some technicalities verbatim. At least it looks like. So let me see, what is the time? 1 minute. Oh, 1 minute. Okay. So there is. I'm finishing very quickly. So there's a dynamic formulation of this, where again you have now an updated thing, an updated term for the losses. So not only you update the drift here, but you update the losses, and the mass that accumulates at the coffin state is given by this. There are these added terms, and you can also relate this to a fluid dynamic formulation. So you can replace the previous problem with one which you have over here. Here you have a Fokker-Planck with losses, and here you have another term that penalizes how much you're losing. And then I just wanted to mention one thing, that there have been some attempts to link such a problem to Feynman-Catch. And so going back to Nagasawa, Polbinger, Leonard, and ourselves as well, we played with this, where a Feynman-Catch rationale is you reweight a measure with something that accounts for the losses. But this does not really address the problem where particles are lost, because this represents the probability for surviving particles. It's again a probability density. You don't have the structure that we thought, that the mass reduces. So the downside is that the upside is that the Schrodinger problem is easier. I have not written it down. The downside is non-physical and inconsistent with Schrodinger's dictum. And these are the reasons. For example, if the ρ1 is consistent with the prior model and the losses, if you solve this problem, you don't get the prior. Like if I give you a prior and I give you the margin that's all consistent, you're supposed to recover it if it's consistent. If you formulate like that, you don't. You have to formulate it like before with the coffin state. And here are some simulations where you have simple diffusion and killing rate, and depending on the mass at the very end. So here the mass at the beginning and at the end are the same. So you see how the Schrodinger transports the mass across. If the end mass is less, you get this expression. Now, if you use the reweighted process using the Feynman-Catch, you have no way of adjusting the V. And this shows the rate of survived mass. And with that, this is the archive version of the paper. And with that, I would like to thank you for your attention.
Any question?
Thank you for the nice talk. So you correlated, or the way that you describe the problem is with this coughing state, but and then the mass disappears. But could one also think that you really have two states, as you said, discrete, and you're just transferring the mass from one copy of your, let's say, RD space into another copy of your RD space. When you think about it in that way, could you do something for multiple copy states?
I don't see why not. You can have multiple, yes, yeah. I mean, I think that again, this is just the very basic problem. There are other layers you can think of, vector valued, for example, distributions, and then different things disappear at different rates or different different ways, and you postulate whatever the physics tells you, and then you try to adjust it, or you postulate whatever from your desired sort of answer to some practical problem, images or whatever, and then you try to smooth it out in a way that makes it consistent.
Hi, so this might be a very silly question, but most of the times we model progressive processes as as measures over time at times on the underlying Wiener space, right? So can we look at the evolution of this measure in time, in the sense that disappearing particles are actually stuck in time, sort of like that?
Stuck in time.
Yeah, so because if you consider 0 to 1, you get the product is also like a probability measure on this.
Yes.
So is there a reformulation where you consider this evolution and the particles just get stuck there according to some rate, maybe a Poisson tick or something?
I mean, this is kind of that.
Okay.
But, that's stuck in time. You can think of it as, I don't know, maybe Yongxin, you might want.
It's not so difficult to understand this. Basically, the way you add the coughing state is here we just add one coughing state to account for the loss of mass. If you want to model some particle get stuck in time, you just say build your coughing state. The coughing state is really RD. So you get stuck there, you just keep there, you don't move anymore. It just just twice as complex as the original problem, but it's doable.
Yeah, various ways. I mean, again, this is just a model.
One last question.
Very beautiful talk. Thank you. And, so I had a couple of questions. So one was, so whether V can be also negative, or is assumed to be positive and it stays positive. So
for this, we're thinking of V positive. The V negative will represent creation. And we're currently working on something along this direction where you have both creation and killing, but it's a little bit more subtle.
Okay.
So in the sense that there is a little bit of a trade-off that now it's very difficult to explain, but how much, if there's a pool that will allow you to generate particles coming in. So there's no a simple answer, quick answer.
Instead of, that rate is like that and birth rate together.
Yeah, in principle, there's no reason why not, but the details are not all worked out. I don't know, Yongxin, you.
Yeah, it's slightly more tricky than this. I mean, the problem is you see, when you consider the reason we consider the killing only is because if the process is killing, right? You know the total number of particles is really at the beginning. You have the number of particles is fixed there. It's just some particle get killed. So, but if you have killings, you don't have a good estimation of the total number of particles. But if you want to use the large deviation theory, basically, the large deviation tells you the probability for something to happen is proportional to e to the power minus n and multiply the rate function. And this n is very important. If this number of particles is also changing, it becomes much more tricky, and we don't have a really good rigorous way of dealing with this. But I mean, computationally, you can do this, it's no problem. But yeah, just
The interpretation.
You can use the theory of relativation to justify this.
Yeah.
Okay, I suggest we stop here. You can talk to Tryphon.